started now. Welcome everyone to the SZ4D International Webinar Series. Thank you all for taking the time to join us across the globe. I'm Anaïs Ferro. I'm the SZ4D Managing Director, and I'll be your host today. Before I introduce the speaker and get started, I'd like to share some quick announcements. It will be very quick. So first, we'll be announcing very soon our speaker for next month. So please keep an eye out for the announcement and the link to register for our February webinar. We are running a scientist matchmaking program to help individuals create new collaborations and share mentorship opportunities. So if you are interested in joining the community of about 140 scientists now from across the globe, I invite you to take the quick survey, which I'll be pasting in the chat in a moment. We do run many activities towards community engagement, and I invite you to visit our website, sz4d.org, where you'll get all our updates and on all our upcoming events. Now, quick housekeeping. This webinar is recorded and will be posted later today on our YouTube channel, which compile also all of our past webinars and all of our recordings. Live translated captions are available. You can select your preferred language by clicking on the closed captions button at the bottom of your screen. And so finally, we'll be using the Q&A feature for your questions, which is also available at the bottom of your screen. So feel free to ask your questions to the speaker, and we'll get to them at the end of the presentation. You can also use the Q&A feature and the chat to introduce yourself and let us know a little bit about you, maybe a little bit about your research. All right, time to introduce today's speaker. Audrey, bonjour and welcome. Audrey Galve is a marine geophysicist working at the Côte d'Azur University in the GeoAzur laboratory in France. Audrey is responsible for the management of GeoAzur's marine facilities, including the Ocean Bottom Seismometer Park, which has now been constituted as part of a new French national park for a year. She investigates how structure and fluids influence slip mode on the megathrust fault in subduction zones, with a particular emphasis on regions such as Greece, Ecuador, and the Antilles. She is currently conducting a project on the Ecuadorian margin, the results of which she'll be talking about today. Audrey, thanks for joining us, and you have now the floor.
Thank you. So let's go. So what I'm going to present today, it's something that is born after the Pedernales earthquakes. So these Pedernales earthquakes occurred in 2016. And thanks to the national network, we discovered that just in this area, we have in a short area, the existence of seismic and aseismic slip. So we just had the project to see what is the geometry of the megathrust fault in this area, and to look for, to try to follow the fluids and look for the circulation of the fluids on the downgoing plate, and also how the fluids circulate on the margin. Yes. So, so there is a lot of people working in this on this project. So first, of course, there is the Ecuadorian group. So I just have the PI of each group, but there is many people working on it. So there is Mónica Segovia, Instituto Geofísico, and also we had the help of the INOCAR. And we had a few laboratories in France, in Sofia, and also in Rennes, Paris, Brest. And the other partners are from Andreas Riedbrock from Côte University, and Michele Paolato from Imperial College. And at the end, Laura Wallace, that at the time of we had the proposal was at GNS. All the data we get come from two marine campaigns we got from the French facilities, and one is the first, the Hyper marine campaign that was in 2020, 2022, and the SUPER-MOUV marine campaign in 2024. And we get funded by the French National Agency. And at the same time, of course, we, Andreas Riblock deployed around 1,000 land stations. The group of Susan Beck and Anne Metzer obtained funding from the NSF to deploy the nodes of Pascal and to record the shot we are made for the 3D grid. So what happened in Ecuador? So in Ecuador here, you have the main earthquake we had on the coast is an earthquake in 1906. It was a magnitude 8.5 earthquakes and erupted the megathrust fault from the north Ecuador and south Colombia. After that, we have several magnitude 7.5, 7.7, 7.8 earthquakes from the south in 1942, 1958, and 1979, occurring along the coast. And the last one was in 2016. It was a magnitude 7.8 earthquake. It's the famous Pedernales earthquake. And so during the Pedernales earthquake, here you can see in blue the rupture zone. So as I tell you, there was this permanent network when there is GPS station and also seismometer. So since there was a GPS station along the coast, we were able to catch the occurrence of slow slip events, and we say here in red. So just in the updip part of the megathrust fault above the rupture area, and also in this area a little bit more to the south. In the same area, the blue part here is also a slow slip event that was studied by Vaca and collaborators. And when we have the slow slip event and also seismic swarms occurring at the same times. So since these seismic swarms are occurring every 2 years, we suppose that these slow slip events also occur every 2 years. So right now, many people have tried to find famous tremors on this area, and we have no insight right now for the occurrence of tremors. So, as I told you, there was this geonetic network. It's very nice. We have around 85 stations along the coast, and it allows to have a very nice constraint of what is the convergence between the Nazca plate and South America. And it also allows to discover that we have a sliver here that escape to the north and take part of the convergence. And this movement is taken by the transpressive system faults here that accommodates part of the convergence, as I say, and with earthquakes having magnitude up to 7.6. So Ecuador is this area of the sliver, the North Sliver, as it's called, is particular because it's made by an accretion of several plateaus, oceanic plateaus, as shown in the study of Ramos and Aleman. And finally, this sliver is partly made of oceanic crust. So what do we have on the Nazca plate, on the subducting plate? So the two main features on this plate is the Grivalja fracture zone that is separating the Nazca plate from the Farallon plate. And the other one is, of course, the Carnegie Ridge that is made by the Galapagos in the relation between the Galapagos Island and the spreading center. So what the other part we observe, the smaller size, it's we observe bending fault, as you can see here. So when we get close to the trench, we can see bending fault. You can see here in the bathymetry. We have the Atacama Seamount here, just north here of the Carnegie Ridge. And we observe also some ridges here that are also subducting. The other point is a lot of fracture zone exists here that is linked to a former transform fault. So the Carnegie Ridge is a very special feature. It's quite huge. You have the elevation is in between. You see it's very different also. The superficies, the elevation is varies from 9,000 meters to 900 meters to 3,000 meters. And it's very variable. And the initiation of this ridge is around 23 to 25 million years, and it's assumed right now that when it's at the subducting area here at the trench, it's around 20 million years. So since so we have this huge ridge subducting, and most people, we know that when you look most to the south in South America, and some ridges we have fat slab. So what do we observe in Ecuador along this fault? So there was in 1994, 1995 there was a temporary deployment on the region in the area. And so if you look at the section B and C, there are two sections that pass in front of the Carnegie Ridge. And you see that we have a continuous seismicity here showing the slab here and here. And this is, you have a dip of 25 and 30 to 35 degrees, and it's going up to 200 kilometers. So more recently, using the permanent network, the permanent Ecuadorian network, RENSIG, Fault and collaborators, they locate also the seismicity in this area. And the same, if we look at the section 2 here in front of the Carnegie Ridge, we found that we have a seismicity showing that finally we have no flat slab in the area. If look what happened close to the trench. So there was this deployment in 1998 where deployed OBSs and also land station. And in this area, it allows to locate the seismicity and to see where is the megathrust in this area. So the megathrust is very shallow, just first due to the fact that we have the distance between the trench and the coast is very short. It's something like 35 to 50 kilometers. And also, since we have this subduction of the Pedernales, of the Carnegie Ridge, we have an uplift and the megathrust is very shallow. So this is a nice area to study since we have this slow slip event and seismic and aseismic slip. And we have also this megathrust fault that is very shallow that we can try to capture using geophysical methods. So that's what we have done. In fact, GeoAzure is working for the past 20 years on the Ecuadorian subduction zone, and we have done several marine campaigns. And for example, in red, you have the MCS marine campaign. We have Sister, Salieri, and Hyper. We have also a high-resolution seismic campaign with Amadeus, Atacames, and SUPER-MOUV. And this is the green lines and the blue lines. And something incredible in Ecuador, there is a petroleum data set. And this is, you can see this very thin black line every 10 kilometers here that are MCS data. So let's have a look to what happened for the megathrust fault geometry going from the south to the north. So if I look at here, you have the south is here and the north is here. And so let's have a look first here. You have this sister profile, when you can see that it was interpreted to have a seamount subducting. And just before we have a length of sediments entering the subduction. making the megathrust fault quite rough. Going to the north, a little bit more to the north, you see that's a little completely different. The megathrust fault is more flat, and it changed quite a lot from a few kilometers. And if we go again to the north, this is much rougher. We have the décollement is very rough here, and so it's a very rough area. If we look, yes, if we look now at this here, we are parallel to the trench. You can see here the change of the subduction. So if we, of course, it looks like it's 664. It's very flat, but we just in a hole, and we have top. So it's a very rough place, but not very. It's usual. It's normal in the way that it's Carnegie that is just subducting, and we have seen that Carnegie have a very rough surface. So going to the north, oops, I'm going back. Going to the north, so we are here to the north, a little bit north of the bathymetric signature of Carnegie Ridge. So here we look at just this MCS profile, and the same. We have cement entering the subduction as Atacama cement here, and we have the one just before the trench entering the subduction, and the one below here that it was imaged. If we go a little bit to the north, outside the effect of the Atacama cement, here we observe a kind of ridge entering. We have here we have a step of around 600 meters with a kind of plateau just here. So if we do this is a cross section going from south to north. So we have this high that is in reality the what we call the Atacama cement, and that is 3 kilometers high. And after we have this plateau here that is around 1.5 kilometers high. So also to the north, we can see that we have a rough interface. So let's see if we try, since we have all the scan data and all the data we have, we succeed to map what is the dimension of this relief entering the subduction zone. So here, for example, we map what is the extension of the Atacama cement. So for example, here you have a scan data. So what we have done is just to map what is really the basement of this, the extension of the cement. It's much larger than what we see on the seafloor. And so we determine the extension of the Atacama cement. We also have the extension on what is the one was just entering the subduction. This is the peaks I show you before. In reality, it's this you have the extension and what is subducting, and the plateau is something here. So knowing that we don't have data here just because the platform is too high and the ship couldn't go there, and so we don't know exactly what is the extension depth of this plateau. At the same time, there was a study from Colo and collaborators for 2022 that shows that in front of Cabo Pasado, we also have on the subducting on the megathrust fault high in this area. So if we superimpose the slow sleep event and the aseismic and the seismic sleep on this structure, so what we see on the north, for example, on the plateau, we have the slow sleep event. This is the aftersleep of Pedernales, and this in green, this is the slow sleep event that occur every 2 years. And there is so we can see that this slow sleep event occur in the place when we have the subduction of this plateau. In the south, we have the same, we observe the same. We have in subduction where there is this kind of high subducting. We also have this afterslip after the Pedernales earthquakes. It's not the case in the middle. Right now, we observe no slow slip event, but where we have this huge subducting relief. And everything, of course, is limited, seems to have limited the rupture of the Pedernales earthquakes. So we, if we superimpose now the coupling, so this is, you have the coupling calculated by Noke and collaborators on top. So it's pretty different if we compare the area. On south, for example, we have this. We have a high coupling where we have the slow slip event and the subducting relief, compared to the north when it's less coupled and it's more. We are more in a transition than in a very well coupled area. In the middle, we are in a very less coupled area. So what can we say about hydration? So if I look at hydration, the idea is to try to look at the bending fault where the fluid can enter the subduction. Since he enters subduction, he can serpentinize the mantle, and after you have the fluid circulation from the fluid, the dehydration of the crust, and the fluid that can travel and through the margin. So let's have a look first at the bending fault. Sorry. So for the bending fault, if we look at it, so we map in the area of the Pedernales earthquake the bending fault. So what we observe is we are going from small scarps to medium scarps for this fault. And the maximum, the medium scarps are located, in fact, in front of the Pedernales earthquakes. So to the north, we have much, the scarps are smaller and the orientation is changing. So you can see we can see clearly the fault in the bathymetry, and some of the faults are just cutting also the subducting seamount. So what we don't have is a very nice evidence of this fault reaching the moho. This is one example, but it's nearly the best one. It's not clear if these faults are really cutting the mantle, the moho or not. Oh, wait, yes. So if I want to have now indication of hydration, the only way with the data we have is to try to derive the hydration of the content of hydration of the downgoing plate just by tomographic methods. So in Ecuador, we have several campaigns. It was we had Sister and Salieri. Here, mainly the 2D profile, some on the Carnegie Ridge and some close to the trench. We had the Esmeralda 3D tomography that was on the north. So you have the Pedernales earthquake in this area, so it's north of it. And finally, we deploy in 2022 the OBSs to have a 3D image of what happened in the area of the Pedernales earthquake. If we look at what at the compilation done by Gravemeyer and collaborators, what happened when we have this bending fault? What is the impact on the P wave and the S wave velocity? So on this image here, you have the tomographic model for P wave velocity in Nicaragua, and here you have the same image for S velocity. The trench is located here. So here you have 1D velocities are extracted. So for the blue one, that's 1D velocity extracted very far from the trench. And the red one are velocity extracted close to the trench. So if we look at Chile, for example, it's very clear that when we are far from the trench, the velocity are higher than we are near to the trench. It's less evident in Nicaragua, but we have also we can see the difference, the blue line being more on this area and the red line having less velocity, less rapid. So what in fact what happened is that in Nicaragua, for example, in Chile a little bit more, but the impact of dehydration on the crust, when you look at P wave, it's not so much. We have few impact on the P wave for hydration. It's not easy to use to look at it. It's really more evident on S wave. You can see here, for example, when you have the depletion of the 3.5 and the 4 kilometers per second. What is more evident to see, in fact, is on P wave is the serpentinization. We have a strong impact on the P wave velocity. Here you can see the 8 kilometers per second being depleted in this area. So what we have? Let's have a look at our seismic tomographic line. So we look at different 2D lines going from the south to the north. So here we are really on the south with a 7 kilometer thick crust. In front of the Carnegie Ridge here you have something having a 15 kilometer thick crust. A little bit more to the north, north of the Pedernales earthquakes, we have something with a normal crust when we are on the subducting plate, is going thicker, being 14 kilometers when we are at the trench, and much thicker when we are below the coast in this area. And to the north here, we come back to a normal thickness crust of 7 kilometers. So what happened first? The first observation is that we can see is the effect of Carnegie Ridge. We have the thickened crust due to the presence of Carnegie Ridge. And so it was normal to see it in front here. When you look at this, it was more not so evident. At the end, we will not expect it to have 14 kilometers next to the French, just in this area. So the point is, where is the northern flank of Carnegie Ridge? And so I reported in this image different thickness of the crust we observe on the using different studies. So what you have is a thick crust in front of the Carnegie Ridge here, as we've seen. Here also on study that was done on far from the trench. Here we are still 11 kilometers. We have the 14 we are talking to get to previously, and 23, and to the north we come back to a kind of normal thickness for the oceanic crust. So so the first clearly we don't have a continuous east-west extension, just following the border here of the Carnegie Ridge. And it's more organized, having a continuous extension in the direction of the 2,500 meter isobat here. Wait, move a little bit. So it's more following this trend. However, another possibility that was that just look back at this image. Having the fracture zone, and in some places, for example, here you have this fracture zone, and this fracture zone has shifted the Carnegie Ridge. It seems to be the same in this area, more or less. We have some places where we have a coincidence between shifted of the Carnegie Ridge and the presence of transform fault. And so one possibility, when it was proposed by Colo and collaborators, saying that if we look at this interpretation of the fracture zone from RD and collaborators, there was this minor fracture zone here that could, for example, play a role. And here it's proposed that, for example, we have the Carnegie Ridge before, and when we are below here, we have this transform fold. We have shifted the Carnegie Ridge that will explain, so we have a shift in this area that will explain also the uplift here we observe and in the Punta Galea area. So this was just more a structure of what is it of the crust, but is not is what happened for the hydration. So this is looking the velocity that it was done previously on Nicaragua. We extracted 1D velocity. So we have you have in green here the velocity of Carnegie Ridge far from the trench. Not affected by bending fault. In fact, that is in this area here. So here it's velocity and depth, of course, and it's based on the basement. And what you have also is Coco Ridge. That is Coco Ridge is also a ridge borne by the same interaction of the Galapagos hotspot. And so the same nature. And so the blue, these two blue here are on the outside. And you have this blue like here, it's when we are close to the trench. And we have also the Malpelo one, which is the orange side. In pink, what I put is what we have, the velocity we have in Ecuador here. That is, so it seems to be, we can interpret it like in Nicaragua when we are off the trench, the velocity are a little much higher than when we are near the trench. It seems to be more or less the same. It means that the impact is not so much. It should be around 3 to 5% of the velocity. They will reduce the velocity by 3 to 5%. When something is more interesting, more intriguing, it's this. You can see this on this tomographic 2D image. So we look here on this line. So this is line A. On this line, we have done a 2D tomographic inversion. You have the result here. So the downgoing plate is a red. Here's a red line. So we have this downgoing plate thanks to a joint MCS profile. And if we look at this, we have this depletion of the 5 km per second isovelocity and the 6 km per second isovelocity. And this we have this low velocity really localized in this area. And if we look at this, in fact, in the corresponding MCS data, we have no evidence of cement. That was the first idea we had. We say, okay, we are in the area where we have the cement subduction, so it's part of the subduction of this cement that is creating probably hydration. But this is, but clearly we have no cement in this area here, and something is if we go back to the study we have done thanks to the post-Pedernales earthquakes deployment. So here you have the map of the deployment with all the land station. And this study was done by Leon Rios and collaborators. And so they obtained earthquake tomography of the area using this data set. So we have the land station here and the LBS on next to the trench. And so thanks to this, they image this low velocity area. So P4 is the line A I showed you just before. We observe the same low velocity anomaly. And this anomaly seems to continue toward the south and be parallel to the trench. So it's probably, so the fact is we are thinking, okay, it's a bending fault. but why this bending fall will react more than the other one. And one possibility can be that it can be a transform fault, not the fracture zone, sorry. It could be the fracture zone here create this, because it's not, it's difficult to use only P velocity to have the hydration. So it could be probably that we see more the deformation that was before in this fault. And we react really to the opening, to the bending of the plate, and react to the bending. And this is, if we continue this, in fact, we are in continuation of this minor fracture zone that was shown by Hardy and collaborators. So this is, for the moment, an hypothesis. And so what we are doing right now, this is the 3D deployment. And what we are doing right now is to invert all the 3D data sets. We have to finish this during the year. And to have really the 3D image of what happened below. So the idea is to have the P wave, but also they have the S wave, because we observe P2S conversion in the area. And this will probably help a lot to understand the hydration of the downgoing plate. So what happened in the upper plate? So if we so we just now focus on the area. So we have 3 marine campaigns, Atacama, Hyper, and Super, where we first we were able to identify the pop marks and all the fleet seepage. So the fleet seepage we're able, because we keep all the data set from what is the name? The pinger, not the pinger. The high resolution bathymetry. We were able to identify where we had a fleet seepage. So we have here the map of this. So the pop mark are in gray. And you have remarkable pop marks that are the red dots, remarkable in the size. And also you have the fleet seepage in the yellow triangle. And so if we look at how it looks like, and sometimes we have this kind of image with a moon, in fact, in having a very high flare. This is 80 meters, but sometimes it's much more, it's 300 meters. We have some places we have the pop marks with a mound in the middle, and also we have small flare going from there. And in some places in the pop mark fields, it's not really flare, it's more diffusive seepage we can see in the water column. So let's have a look at what is the correlation between the structure we have and this what we observe on the surface. So we will first look at this area when we have this relief below the margin, and at the same time it's the area we are here. So if I superimpose both, we can see that we are just in front of below the above. So the pop marks and the fleet seepage are above this relief, this entering the subduction. So if I look at this fleet seepage here, it was active in 2012. We can see this 300 meters high, and it was still active in 2020 here with a 400-meter high. And we look at the seismic line here. We have the seismic line here, so we have the field of pop mark all along this area. And what we observe is we have in some places the attenuation of the reflectivity in places where we have fluids going outside. And we have some bright spots here located, and at the same time, deeper, we have attenuation of the reflectivity in some places. So in this area right now, we cannot go deeper to see what happened deeper. But let's go to the north, to the south. I can't remember. So just yes, we just let's go a little bit to the north right now to see what happened in the area when we have the slow sleep event here. And in this, but no, I'm going back. Voilà. In this area here, we have so it's a special area in the way that it's an area where we have the initiation of the slow sleep event. So in this area of the initiation, at the same time, is the area where we have these pop marks and also fluid seepage. So if we look at this at the seismic line, we have a seismic line going through here. So if we look at the seismic line, what we observe also is we have a fluid seepage, and we have this reflectivity anomaly where we have shifted. And we observe also, this is the interplate here, and we observe a band of reflectivity in this area, in the interplate. So what can happen in this area is that we know that when we have the subduction, we have in this area, for example, we have overpressure fluids, and this creates at one point the slow sleep event. And when the slow sleep event occurs, this barrier here stop, and we have the fluid that can go through and can be seen on the upper plate. So going to the south now, if we look here, so it's the place where we have this subducting, and we have also the afterslip. So we have a seismic line here. That this is a MCA. We have the seismic line going deeper, so we can image here the megathrust fault. And when we image the megathrust fault, we can see here we have this fault that seems to be connected to the megathrust. And this fault here, we have a zoom here, and this is the fault. And after in the fault, we have here bright spots along here that seems to be a fluid accumulation. So in fact, what we suppose is we have a fluid migration along the fault, and the fluid escape, and we have after an accumulation and migration along this stratigraphic contact. We can see here we have the attenuation here in places where we have fluid seepage. So the point is, for the moment, we know we have something entering. We know that we have fluid escaping here, but the relation between is it coming from the interplate or not is not really done. So if I look at everything together, the idea is more that we know when we look at all the seismic data, we know that when this relief are below are entering, they of course created a lot of cracks. So the margin is very fracturated. And we have also sediments entering, probably sediments. We are not clear evidence right now, but probably we have lenses of sediments entering just after and just in front of the cements. And this, due to this, we can have cracks and circulation and fluid escape on the margin. So everything is probably due to the roughness of the Carnegie Ridge. It's very rough, and we see that it's created all the fracturation of the margin. And as I told you before, so everything is above the Pedernales earthquake. Also, everything happened on the updip part of the megathrust fault. And yes, what I told you is that we have a missing link between what we observe on the surface, what is going through on the surface, and what we have. Is it coming from the interplate, or is it coming from much less deeper? So this was one of the objectives of the SUPER-MOUV marine campaign in 2024. So we use this. You have the submarine, Le Nautile, from the Ifremer, from the French marine facilities. And so inside, we can have one scientist, and you have two people to drive it. And this one, he can dive up to 6,000 meters. So we went here on the margin up to 4,000 meters. And the idea is to just sample the fluids and to do some fluid geochemistry and to have really the origin of the fluids, and can we have a continuation between the fluids on the interplate, and do they escape, and was there the implication of this. So this is some image we made with the Nautile. So we observe the fluid escape. In some places you have the bubbles. When we have these bubbles all the time, we have you see here the concretion. For example, here it's a huge concretion on one of the. It's what we observe when you have this moon in the middle of spot marks. So it's huge concretion. And you have this in places when you have the fluid escaping, you have the bacterial activity. So for the next year, the idea is really to work on this. We will finish the 3D, so to constrain really what happened in P and S wave for the ongoing plate. And the idea is to have the continuation in between what is going down and what is going through the margin. There is really similarities between Ecuador and New Zealand, and that's why it was the idea to work with New Zealand, is to make after a comparison to see if we can see a general characteristic in between both subduction that is really driving the seismic and the aseismic slip. Thank you very much.
Thank you, Audrey. Thank you very much. I think we have time for a few questions now. So if you would like to use the Q&A, any questions from the attendees? We do have a question from Kellen Wang. Thank you, Kellen. How is the upper plate moho imaged?
Well, it's not. We don't know. In fact, that's the point we have. I'm not sure I have something. Yes. So right now, probably it's where we on land. The connection between the upper plate moho and the ongoing plate is probably on land. So we had studies here from the Americans, and they look at seismic at doing a receiver function, and so they put the moho in this area here. So in this area, they put the moho at the upper plate at 18-kilometer depth. So this is the most probably the most constrained part. There is less constrained with tomography at a very large scale, and in this case it's very deep, and it's probably not constrained in this area. It's almost at 60-kilometer depth. So if we suppose that the moho is at 18-kilometer depth, it means that on hyper E, for example, when you look at the seismic line here, the connection is probably just below the coast.
Thank you. We have another question from Athanasios Ganas. Thank you, Athanasios. Thanks for the talk. What is the seismic velocity on the top of the slab?
You mean on the interplate?
Yes.
Yes. We don't know right now. We expect to have it. Well, we are waiting for the 3D image. Right now, we didn't inverted the reflection. So the idea right now is to also do inversion of the reflection phase on the interplate to succeed to constrain what is the real depth of the interplate, because it's easy when we are at the beginning, but when we are going deeper, it's complicated to have the real velocity. And so the idea is to constrain like this.
Okay. We have another question from Martin Sherwood. Great talk, thank you. Did you see any evidence of subduction channels, sediments above the décollement with potentially enhanced fluid flow? I did not see anything in the images, but might have missed them.
Yes, yes, I forgot something. Yeah, I'm so used to work in this that I forgot to say that it's erosive margin. So in fact, the sediment thickness is maximum. Well, it's around 1 kilometer. So it's there is nearly no sediments, and we have no evidence of subduction channel like a very thick sediment subduction channel. It's more to the south. The south, really, the south of Carnegie Ridge, we have it, but not in the area of the Pedernales earthquake. It's really a erosive margin.
Yeah. Any more questions for Audrey? Going one, going twice. Yeah, I think we are done with the questions. So just a reminder that this webinar has been recorded and will be posted later today on our YouTube channel. Thank you very much, Audrey. Merci beaucoup for your time, for participating in our webinar series. And thank you everyone for joining us, for taking the time to come and ask your questions to our speaker. We'll be announcing our next month's webinar through our listserv. If you are not receiving our listserv yet, I encourage you to subscribe to our communication. Visit our website, SZ4D.org, to subscribe. And I wish you all a good day or good night. Bye, everyone.
Thank you very much.
Thank you, Audrey.
Bye.
Bye.